Hello everyone, today I want to present my project Mizu.Pot. Let me introduce the idea in one simple sentence. Mizu.Pot combines image recognition, environmental sensors, and AI-driven recommendations. It sends real-time alerts to the users. For example, when the soil is too dry or the light is insufficient or the water tank is low, the user then receives clear guidance to create the perfect environment. In short, this is where IoT meets AI for the future of smart, easy plant care. To connect all components of our system, we needed efficient communication protocols. So we choose two main ones. The first is REST web services, which are flexible, scalable, and perfect for exchanging data across microservices. And the second is MQTT, which is lightweight and real, ideal for IoT. It allows our sensors and devices to send updates instantly using minimal bandwidth. By combining these two, we ensure smooth communication between devices, services, and users. Here you can see our system diagram, which consists of different sections, for example, microservices, catalogs, things to speak, etc. Here's how the overall system is structured. Our platform follows a microservice architecture developed with Docker containers. This design gives us modularity and scalability. We implemented multi-threading to speed up heavy tasks like image recognition, also asynchronous API calls, so one slow services won't block the others, and independent containers, meaning each service can run, restart, or scale without affecting the rest. This makes our system robust and adaptable. In this section, as you see, we want to talk about our catalogs. The first one is service catalog. To organize everything, we created two catalogs, as I said. The first is service catalog. It's like a registry. It stores addresses of microservices and MQTT broker details. Other services use it to discover each other dynamically. The second one is resource catalog, which stores structured data about users, devices, and races. It ensures a single source of truth, so all microservices work with consistent data. These two catalogs guarantee smooth coordination across the platform. In this part, we want to talk about external integration, or as you can find here in the picture, third-party services. The first one is Docker. For deployment, we relied on Docker. Each microservice runs in its own Docker container, isolated from the others. This gives us portability, easier scaling, and higher reliability. Using Docker Compose, we can manage multi-container setups, and every service has its own configuration. With Docker, we ensure modularity and kind of eliminate single points of failure. The other, our third-party services that we use here in this project are Plant ID and Gemini. We also integrate these AI services to make our system smarter. So with Plant ID API, we can identify the plant species and even detect diseases. Then using Gemini, we can enrich the user experience by providing optimal range for light, humidity, and temperature. Also, a simplified, user-friendly plant name that will suggested by the AI, and the AI-generated care tips. This combination makes plant care highly personalized and intuitive. Okay, now we want to talk about the hardware and device connector. Here we use ESP32 and sensors. Our setup is based on ESP32 microcontroller, which is powerful and energy efficient, and it supports deep sleep for low power use. It connects to to sensors for soil moisture, light, temperature, and water level. A water pump is also included for automatic irrigation. The ESP32 runs on MicroPython, which allows flexible programming and MQTT communication. The device connector software handles registration, configuration, and real-time publishing of sensor data. Now we want to talk about microservices. As you can see here in this diagram, our system has several microservices that we want to talk about now. The first one is bot notifier. This service is the communication bridge with the user. It listens for alerts like empty power tank and sends a Telegram notification. This way, users always know the condition of their plant without opening the app. The second is chart service. The chart service turns sensor data into visuals. It retrieves historical readings from ThingSpeak and generates clear graphs of soil, light, or temperature. This helps users quickly see how their plant's environment changed over time. The next is data analysis. Here, we transform raw numbers into insights. The service computes average and detects threshold violation and even estimates water usage. The results are then summarized for the user, so plant care becomes data-driven and easy to follow. Recommendation service. This service provides personalized advice. It combines plant identification with Gemini to generate tailored care tips. For example, when to water, ideal temperature, and light preferences, always in clear, user-friendly language. Image recognition. This service identifies the plant from a photo using Plant ID API. Image recognition. This service identifies the plant from a photo using PlantNet API. It returns the most likely species and confidence score. This ensures all recommendations are specific, since different plants have different needs. Waste control service. The waste control service is the decision maker. It compares real-time sensor readings with the thresholds and decides when to act. For example, turning on the water pump. This ensures plants are watered only when it's necessary, and it's avoiding under or overwatering. Firebase adapter. The Firebase adapter service acts as a bridge between the MQTT network and Firebase, and it ensures real-time data storage and analysis. ThingSpeak adapter acts as a bridge between the IoT and IoT smart plant and ThingSpeak cloud, and it tries to monitor and visualize the trends. One of the new services that is added in version 2 is Plant Health. Uh, Beyond just monitoring, our system also acts as a plant doctor. Often users can see their plant turning yellow or weak, but don't know what is the problem. The plant health service solves this problem. It tries to receive the image from the Telegram, and now I want to introduce one of the new microservices that we added in this version 2, which is Plant Health Service. Here, users can upload an image of their plant. The system integrates with plant.id API to detect potential diseases and provides probability scores. Then it uses Gemini to generate personalized treatment advice and offers clear steps for recovery. This service makes the platform proactive, helping users diagnose and treat problems before it's too late. Admin analysis service. To give administrators full control, we built it to monitor the dashboard. The admin analysis provides real-time statistics, such as users, devices, and active connections. It subscribes to MQTT sensor topics to display live data feeds with timestamps. The dashboard, built with Dash Python, refreshes automatically every 30 seconds and offers interactive charts. Admins can track plant types, user engagement, and system performances easily, which helps in troubleshooting and improving the platform. Mock script. To develop and test without hardware, we create mock scripts. The mock scripts module simulates realistic device behavior. It generates fake sensor data like soil moisture, light, water level, etc. So developers can test the entire ecosystem. It also has a graphic user interface built with CTK where values can be adjusted manually. This helps us debug services and validate data flow and work independently of physical sensors. Plant community connector. And finally, we added the community aspect. The plant community connector recommended relevant Telegram groups based on the type of the plant, for example, indoor, outdoor, or cactus. It connects users with people who share similar plants and encourage them to exchange tips, experiences, and advices. This makes plant care not only smarter, but also more social and engaging. Okay, now let's check the system together. As you see, we are in our Telegram bot. Click Start. See the login message successful. Click on Add a new smart ways. Here we have a message for device registry. Click here. Okay, we see the message, the device registered successfully. Okay, click on see the list of connected smart wastes. Waste device 4. Click on this. Ask to would you like to set it up? Yes. Okay, now we need to send a picture of our plant. I choose this one. Drag and drop. Send. Okay, here we'll see the output of the combination of the two microservices, image recognition and recommendation service. It gives us the plant name and categorize it as an indoor plant type, and the parameters and the suggestions. Here it shows us the community plant community microservice and suggest us to be a member of this group. If I click on it, I already joined, so there is nothing here for me. Okay, if now we want to see the waste list again, click on this one. Let me run the mock script. Okay, this is the panel of the mock script. It's a virtual device simulator, and it generates realistic data like temperature, light, as you see, and it allows us to test all microservices, data flow, and decision logics, and etc. Okay, now if I click on this, you can see here the activity log. Oh, first I need to choose, sorry, then. Okay, here we see the activity log, the outputs. Okay, see, here we have all these sensor data that we generated here as well here. Okay, if I click on one of these values, it suggested me to generate the data for 1 day, 30 days, last year, 7 days. And if I, for example, I click on this 1 day, it make me, because 1 day there's not that much data, just the 1 point. Okay, let me see another microservice, which was admin analytic. Okay, admin analytic microservice is an admin dashboard which is generated with a dash in Python, and we have all the necessary information for the admin. For example, a system overview, device status distribution, plant types, and recent activities, real-time sensor data as well here. Now, let me show you the other microservice, which is plant health. Okay, if click on it, it asks us to send an image. Okay, this is a picture of a sick plant that I want to send to this microservice. Okay, with the help of plant ID and Gemini, we have these kind of health issues detected. For example, water deficiency and the others, and also it gives us a treatment recommendation to have this plant. Also, if let me okay, if I send a picture which is not a sick plant, it's fine. It gives us this message. Plant health assessment gives us that our plant appears to be healthy and that there is not that much specific treatment for this plant. Okay, thank you for watching the whole system with me. Bye bye.